This is my code for the Raspberry Pi project. I'm going to explain a little bit here. So we've got our main loop. These functions here, they come from the SPI library. This library is really basic. Starts our SPI here, sets up the chip enable and the megahertz. And then these are our MCP23S17 and using the address pins on them. So there's 3 of those chips total. This resets the 8088. This will hold the 8088 here. It even waits for the holding knowledge right in this loop. Writes a memory array. Needs an address, the code, and the length. Reads a memory array, address, the array you're going to store it in, and the length. Reads a byte, writes a byte, writes memory word. This reads the video memory. This actually reads every other byte because 1 byte is for your color codes. So that's the library, and you can adapt that to any application. So my application that boots DOS, come in our main loop, starts the SPI, it opens up the BIOS file and loads it into a array. Comes down here, this is our array for our jump code. This is just the opcodes here, so EA is jump far, then this is backwards. So F000 to 0100. So then we come down here, we hold our 8088, we write memory array, this is our jump code. We write a memory array, this is our ROM, our BIOS. Then we write a byte. This is to make sure the stop byte is not 0. If this stop byte is 0, it signals the Raspberry Pi to stop. And then also interrupt 13, which is your drive reads, we set that to F as well, so that it's not expecting a drive operation. And then we stop our hold, we reset it, we start this thread with our screen, we start the thread with our keyboard, and then we have our main thread here, which, while the stop flag is not true, it loops. So we declare a character here, and our interrupt command, timer tick. So in here we hold the 8088, we read the video memory, we read the cursor position, and we check the stop byte, and then we stop holding to let the 8088 run. If the stop byte is 0, then the stop flag is triggered to true, and then the next time it loops, it'll kill the program. We pause for a bit, and then through here, this will do this 30 times. It'll check, there's a keyboard buffer in the C code, and if it's got a key to put in, it'll insert the key. We pause, timer tick plus plus, we hold, we insert the timer tick here, and then we also check for interrupt 13, that's your drive operations. If interrupt 13 is not FF, then we execute interrupt 13, and then we pause again. And this is the end of the loop, so back up at the top, if the stop flag is not true, it'll loop. If not, then it kills the screen loop, the keyboard loop. Ends, this is end curses here. and ends the program. So that's how we do our timer ticks and our keyboard inserts right there. And we update our screen here. So you come down, let's just look at insert key. So these are our character tables. So to update the screen, it clears the screen. It's got our rows and columns, how many we got. And while the stop flag is not true, this will loop forever. It takes this character array here, and it prints the characters to the screen, and it does it that many rows, that many columns. Just loops forever. So the character array is updated from this video mem right here, vmem. That is what's updated from the main loop where it reads video memory vmem. So this is just updated repeatedly and repeatedly over and over and over. And then this is what actually prints it to the screen. Down here we got our drive operation, so interrupt 13 right here. Holds the processor, reads which command was actually given, and it checks what drive was called, so it's a A or C drive. Comes down here and says if the interrupt is not FF, it's going to check for the, if the drive is 0, then it's going to get the A parameters. If it's 80, then it's going to get C parameters. Then it's going to read a chunk of memory right here. And this is the interrupt 13 data. So this is what was requested. So whether it was a read or a write, it passes it into that code section right there at the beginning of F0000. You can see we read a few bytes here. If the command is 0, it doesn't do anything. It's right here. The BIOS does all the work, resets disk, nothing to reset. Because there's no disk to reset. It's a virtual disk. If it's command 01, once again the BIOS does all the work. It gets the status of last operation. So it just returns OK, basically. Then we got our drive read here. So it takes, this is out of the interrupt 13 data, which is read right here. It gets your cylinder sector head, bytes per sector, sectors per track, number of heads per cylinder, so it's all your disk data. And it computes this down to logical block address. You got your buffer address here. And then it opens up the file, so right here, the file to open. If the drive is 0, it opens up drive A. If its drive is 80, it opens up drive C. So we seek logical block address times byte per sector. That's where it's going to read from. It reads it into this array here called drive. And then we write it right into memory at the buffer address, the drive, and the size of the drive. So command 3, there should be a write command here. So it's all the same stuff, but instead of writing to the memory, this one writes to the disk. So we read the buffer memory from the 8088 and writes it to the disk. Down here we've got 8, command 8, we got it's getting the disk parameters. And so it just goes disk parameters and stores them in memory, and then the BIOS gives that back to the operating system. 15 does the disk type, and then right here it just ends by putting FF into the control byte for the interrupt. So we only support 15, well, that's hex, so it's not actually 15, but 8, 3, 2, 1, and 0. Every other command is actually ignored and then just reset. So it's kind of limited. So we've got our insert key here, so it holds the processor. It gets the character tell, it reads. So this goes through the keyboard buffer, and it basically finds where to put the key into the keyboard buffer, puts it in, and then releases the hold on the processor. This is the keyboard code on the Raspberry Pi side. So this just runs in the background in a loop, and every time you push a key, it pushes it into a keyboard buffer on the Raspberry Pi side. So it's really a basic system. It does have major limitations because of how simple it's written, but it just demonstrates how you can get up and running. I'll show you the BIOS here. So this BIOS basically complements the Raspberry Pi code. So in the beginning of the BIOS, we've got times in hex 100, and this is an I/O area, and this is like where your drive commands are put and your stop byte is put. And I made it 100 so that we could put in more. We had room for more commands later. So this is why we jumped to 100 in our jump code. You can see here we jumped to 100 because that 100 is actually that area for IOs. So you can see we've got our bit 16, CPU 80, 86. This is kind of important. So when you compile, it'll kick it out if it's not compatible with that processor. And we originate at 0. So we set up our stack. This is important because you can't call anything if your stack is not properly set up. I mean, if you don't set it up, it's somewhere. It may be overriding code if you don't. I clear the interrupt vector table. This is not necessary, but what it does is it fills it all with zeros. And this way you can look at it and see what DOS installs in there and then which ones are blank. See, the RAM, when you first turn it on, it's got random data in it. So by zeroizing it, you can tell what's in there and what's not. So then we load our interrupt vector table, we load the BIOS data area, clear the screen, print the message. Then we set up our segments here. We jump to this boot drive right here. Really don't need that jump there, but it's there because I use this area to add code to test, like, if you're not going to boot with a disk. I load at 7C0. That's kind of the standard. Go through, we set up our interrupt, and we call interrupt 13. And then we reset all our segments to match 7C0, clear out our registers, and then we jump. So this loads the first sector of the drive and gives control over to the operating system. So these are our subroutines for clearing the vector table, loading the vector table, loading the BIOS data area, printing a message, clearing the screen. So this BIOS data area, this actually gets copied at address 400, but this is just what you call like a template, I guess. We got our no COM ports, no parallel ports. Our equipment flags. That's just what I've put in there for now. DOS does kind of look at this. We've got our manufacturer test, memory size, our IO RAM size. So some of this stuff you don't need, some of it do. I had to play with this a bit till I got the DOS to actually boot, so some of these things are required. This is our keyboard buffer here. Like I say, this isn't actually where this is just the template that's copied into the BIOS data area. So this is our interrupt vector table. So all our interrupts are in segment F000, and then here's the offset here. So this is the label, and so that copies that address in there. These do nothing other than prints I00 to the screen and halts the processor so that you know the divide by 0 was called, but we have no interrupt to handle it. Same with these, we go through. So you can see this is where your IRQs would actually be your 8 and 9. This one I'm pretty sure is your system timer, this one's your keyboard. But see, the Raspberry Pi handles that, so we don't actually need to have interrupts in here. Some of my earlier designs I did have an interrupt controller, but it works a lot smoother to have Raspberry Pi do it. So really there's nothing until you get down to the interrupt 10. So this teletypes to the screen, and that's the only thing interrupt 10 does right now is teletype. If you call any other type of interrupt 10, well, it's going to just do nothing. And that, it's actually interrupt 16. It's 10 in hex. So it does handle backspaces, line fees, enter key. So this is interrupt 11 or equipment check. All it does is reads the word at the equipment list. Interrupt 12 reads the memory size. These are called by DOS. So I had to kind of reverse engineer the BIOS. Whatever DOS was asking for, I had to come up with an interrupt for it to handle. Interrupt 13. So this is how the drives reads here. So you've got, it comes in here, it compares the drive to 0, it jumps to start, it compares to 80, so it's looking for A or C, and it'll jump to start. If you actually comment these out, that's all you have to do to turn off the C drive. And if you download the files, these are commented out already. So you'll only be able to boot an A, and all you have to do is change these out and recompile, and you can boot a C drive. So anything else that comes out jumps to not a drive, and then it just exits, so it just views it as not there. So then it comes through and it compares the high side, so this is what command is trying to be called, so 0, 1, 2, 3, 8, 15, and it runs that operation there. So not a drive, it comes through and it just exits here. So resets the disk. It doesn't do anything because there's nothing to reset. Status of last operation, it just returns a successful status. This could create errors because it always returns a successful status. So read-write drives down here, it goes through and it stores. This is where the Raspberry Pi reads from. So it stores the number of sectors, the cylinders, more cylinders, data, sector, head, drive. BX and ES, this is where your buffer is that you're either reading or writing to. It comes down here, it pops AX, it stores the command right here, and then it waits for the Raspberry Pi to do its loop. So it will just loop infinitely until this equals FF. And this is that command that's at F0000. So this gives the Raspberry Pi time to do its thing, and that's over here in the C code. And then when it's done doing its thing, it comes down here, it restores this, and it returns from the interrupt. Something I learned with this is interrupts it stores the flags and retrieves the stags when you call it the flags when you return from the interrupt. So if you have a failure, the carry flag is triggered, and so you actually have to modify that. So that's ends with carry flag here. Real quick, so this is like your parameters. It stores those as well for the Raspberry Pi to handle. Disk parameter stuff, hard disk parameter stuff. So you actually have to modify where your stack is, and you modify the flag byte, and that's how you change that carry flag to be successful or failed. So we cleared our carry flag there. Anyway, so 14 doesn't do anything. 15, this is your cassette. I think it also does something else besides cassette on different BIOSes. But it's just showing that the cassette is not present, not supported. And then this goes through, and this is how you tell your carry flag that it's no good. Interrupt 16. So this is getting keys from the keyboard. So this is where the operating system gets the keys from the buffer area. Goes through, and so it gets your keys through here. You'll have to read through that. Printer, nothing. Resident basic. This does nothing other than prints I18 to the screen, so you know what it was called. Interrupt 19, it jumps to the bootstrap. So this is like a software reset. So time of day, this basically reads the word that the timer clicks. This is where you actually don't need an interrupt controller at all, and you actually wouldn't need the timer clicks either on the Raspberry Pi side. You could actually tell this interrupt 1A to increase the timer clicks every time it tries to read it, because this is what DOS reads to update the timer, is this 1A. So that's your timer. This is a keyboard break, timer tick. So these two don't do anything, they're not required. Video initialization, nothing. Disk parameters, nothing. Video graphics here, nothing. So there you go. This here is dump registers. This is I don't even know if I use this anymore, but this is, if it called instead of doing like I1F, I could also call dump registers afterwards, and it would print to the screen AXDX, CXBX, and print what was in those registers to the screen so that I would know what DOS was calling. That's how I reverse engineered to boot DOS. So anyway, that's the code. You'll have to review it on your own, but I've had some questions about how do we boot DOS without having an interrupt controller, and the best answer is it's done through software. Well, thanks for watching.